Okay, so today we are going to be evaluating an integral from the 2020, I hope so, Berkeley integration bee. And so it looks something like this ridiculous integral from negative infinity up to infinity of 2020 to the power of negative absolute value of x, everything divided by 1 plus 5 to the power of x sine to the power of 5 of x, and that's all dx. Okay, so how the hell are we supposed to solve this problem? Well, what you see here, what you at least should see in the first place, is that we have symmetric bounds of integration. So maybe something like odd even decomposition would work here. You remember hopefully that the integral on a symmetric interval of some odd function is equal to 0. Well, maybe you could use some stuff like this. I mean, not exactly this is what we're going to be using. However, we will use a similar trick to this one. So first of all, well, what kind of function is this 2020 to the power of negative absolute value of x? So 2020 to the power of negative absolute value of x. Well, this function is actually even. Let me just check it for yourself. If you were to plug negative x for x, well, the absolute value of negative x is just the absolute value of x, and so f of negative x is equal to f of x, and so, well, by the definition, 2020 to the negative absolute value of x is going to be an even function. Well, what about the denominator? Well, what is this arc sine to the fifth of x? Whatever the hell it would look like. So arc sine to the fifth of x. Well, we know that sine is an odd function, so if we were to plug in negative x for x, our sine of x would pretty nicely change, yes? So sine of negative x into negative sine of x. And so if we now were to raise both sides of this equation to the fifth power, we would get that the sine to the fifth of negative x is just nicely equal to negative sine to the power of 5 of x. But now, pretty nicely, arcsine is also an odd function, and so we see that the arcsine of negative sine of x is going to be negative arcsine of sine to the fifth of x, and so we get that this entire composite function we've got right there, this arcsine of sine, this is all going to be odd. And I would like to show you guys a neat trick right now. So there is this, in my opinion, fascinating, like real fascinating thing. If we were to evaluate an integral, well, that's an awfully looking integral sign. Now it's a little bit better, yeah? So between some negative a and a, those are our bounds of integration, and we would like to integrate f of x divided by 1 plus some constant b to the power of g of x, and that's all dx, with a slight caveat that I would like to say that f of x is going to be an even function. I would also like to say that g of x is going to be an odd function. You probably already see the resemblance between this thing we're trying to evaluate here and the stuff in the original problem statement. It is pretty much the same, just for the case of f of x being equal to the 2020 negative absolute value of x, and that arc sine as the g of x. Okay, so first of all, I would like to denote this integral as some kind of an I, just for clarity's sake. I don't know, people just like to do it, and I also like to do it. And now, well, what would I like to do here? Well, let's just kind of use the properties of those functions that we know, so that f is even and that g is odd, and let's make a substitution of x being equal, or maybe just x changing into negative x. So we will see that this substitution will actually flip our bounds of integration, because as x was equal to a, well, negative x is going to be equal, negative x is going to be equal to negative a, and also as x was equal to a, negative x is going to be as x was equal to negative a, negative x is going to be equal to positive a, and I would like to make it some different color so it stands out, let's say orange, and move it right over here. And so this substitution right over there is going to give us something like this. It's going to give us that our integral, which I denoted as I, is now equal to the integral from positive a up to negative a of f of negative x divided by 1 plus our constant b to the power of g of negative x as all negative dx. But now, well, we can get rid of this negative dx right over there just using this negative sign to flip our bounds of integration. So let's go on and do it. We will get the integral from negative a up to a, and now of what? Note that f is an even function, so we can just kind of ignore this negative sign over there, just, well, rewrite it, I think, as f of x pretty nicely. And now what about the denominator? Well, we know that g is an odd function, so we can just take this negative sign out of g, yeah, in front of it, getting 1 plus b to the power of negative g of x as all positive dx. And now I'd like to introduce a neat trick there. I would like to go on and pretty nicely multiply both the numerator and the denominator. I wanted to say both upper and lower hand sides. So yeah, let's say it like this: both lower and upper hand sides by b to the power of g of x, by b to the power of g of x. It does not change the value of our integrand. Well, we are just kind of multiplying everything by 1, so everything stays exactly the same. Lovely. And this is going to be equal to what? That's going to be the integral from negative a up to a. And now this b to the g of x is the multiplicative inverse of this b to the negative g of x, and so what we're gonna get in the denominator is going to be well, not 1, is going to be b to the g of x, and then plus a 1, and in the numerator we're going to get f of x multiplied was supposed to be a dot, by b to the power of g of x, and that's all going to be dx. I've got an awfully sore throat, so I've got you know, my milk with honey here, just don't mind me. I'm actually getting a bout of videos for the next week, so you're probably going to be, you know, seeing me, you know, taking a few sips per video for another week, so enjoy it. And now what I would like to do is kind of, well, make another trick. So I would like to add this integral, which is equal to I, as you probably know, to the original version of I that I you know, had before all of those manipulations I did to this poor integral. So I would like to add it to the integral from negative a up to a of f of x divided by 1 plus b to the power of g of x dx. Is exactly what we started with right there before all those substitutions and stuff, yeah? So now, doing the addition, we would like to get, or we actually do get, that double di is equal to the integral from negative a up to a of, that's gonna be f of x, and now I'm gonna just factor it out. I'm gonna get 1 plus b to the power of g of x, and everything's gonna be divided by, well, oh man, that's pretty nice. Those denominators are exactly the same. I should have used pink here. Yeah, so those are exactly the same. So what I'm gonna get there is just 1 plus b to the power of g of x dx, but, well, now notice that those pretty nicely cancel each other out, this factor in the numerator and the entire denominator, and so what I'm gonna get is just the integral from negative a up to a of just f of x dx. But now, well, we know that f of x is an even function, and whenever we are trying to evaluate the kind of an even function on a symmetric interval, it's just perfectly the same as just taking this integral, cutting it in half, and just multiplying the integral by 2. So this is exactly the same as just multiplying the integral from 0 to a of f of x by 2, but now we can just go on and divide out those 2's here and here, getting overall that our original I was equal to the integral from 0 up to the a of f of x. It's not a perfect f here, now it's better, dx. And so, well, pretty neat, I think, because now we can just use it to solve our original problem. And so we see that we can just kind of use our 2020 negative absolute value of x as the f of x. I'm going to say is going to be my f of x. And now 5 to the arc sine of sine to the fifth of x is going to be my b to the g of x. That's going to be my b to the g of x. And so it will all mean that I can just rewrite the integral from negative infinity up to infinity of that 2020 to the negative absolute value of x all over 1 plus 5 to the arc sine of sine to the fifth of x dx. Oh, that's... now it's better, as just the integral from 0 to infinity of 2020 of the, the negative absolute value of x dx. But now, well, we see that whenever x is between 0 and positive infinity, the absolute value of x is just x, so we can drop it and just rewrite this integral as the integral from 0 up to infinity of 2020 to the power of negative x dx. But now, just taking the antiderivative, as we probably should know from calculus, is going to be nicely equal to 2020 to the power of negative x divided by the natural log of 2020 evaluated between 0 and infinity. I should have been more rigorous and just take the limit as t approaches infinity and then evaluate it between 0 and a t, but I think you know where I'm getting at. And so this is going to be what? Well, we will get 2020 to the power of negative x as x approaches infinity is just going to be dragged down to 0. And when x is equal to 0 is going to be, I should have put a negative sign there. And so then it's going to be negative 1 over natural log of 2020, and so it's going to be just the reciprocal of the natural log of 2020, and that's exactly what we're supposed to find in this video. So let's once again go over what we did here. So we were supposed to evaluate this beast right there from the Berkeley tournament, Berkeley integration B, and then what I introduced to you was a trick which is actually called the odd-even decomposition of an integral whenever we have some kind of a even function f and some odd function g, then the integral from on a symmetric interval of f of x divided by 1 plus some constant b to the power of g of x is just nicely going to be equal to the integral between 0 and a of that even f of x with respect to x. And so then we just plug this nice fact we knew there into our original problem, getting that it is going to just come down to 1 over the natural log of 2020. I hope you guys enjoyed it and see you in the next one.